Mr. B. Dhanasega is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We have the subject theory of computation. So in the previous episodes we are studying the Turing machine. The Turing machine, that is how we are constructing Turing machine for that is recognizing few languages which are recursively enumerable, which is going to be the language of the Turing machine. And also we have seen some computation, like that is how we are adding that is numbers or doing proper subtraction of two integers to get a positive result. And that is also we have seen some problems also, how we are that is multiplying by 2, which is going to be much simpler than multiplying 2 that is any random integers. And moreover we have seen that the language of the Turing machine is recursively enumerable, but if the Turing machine is expected or guaranteed that always it is going to be a halt, either with accept or without acceptance, then we will be calling the language as recursive. So which is equivalent to have a problem for which algorithm is always existing. If you want to claim that the algorithm is always existing, and then it is really needed that the problem should, that is the Turing machine should halt always, either with acceptance or without acceptance. As long as we reach the final state of the Turing machine, we can claim that the string has been that is accepted, and if you find that the Turing machine is halting without reaching the final state of the Turing machine, then we can say that the input is going to be rejected, and but still the Turing machine halts. So in either case we call the language as recursive, and if the Turing machine is not guaranteed to halt always, suppose if the input is valid one, it is always halting, and if for invalid input, and if the Turing machine is not expected to halt, then the language is called recursively enumerable, and for those kind of problems we can't claim that the algorithms are existing. So these are the things we had seen as far as the previous episode of this group of lectures are concerned. And now we have there is a variant of the Turing machine with multiple tracks. So for example, like the standard version of the Turing machine is having a single track, always it is possible to store symbols, and a variant of that we have seen in the previous episode is the Turing machine tape with the finite control storage. That is, we can record one or more number of symbols onto the finite control, so that can be later reused for some other purpose, either for comparing or for even recording. So those things can be that is done provided there is a space available, or there is a storage, or there is one or more number of storage locations available on the finite control. And we have seen a few problems also which are very easily solved with the help of the storage on the finite control. So now here we have a Turing machine where there is a single tape available, but the tape is having multiple number of tracks. So every time, that is when you read a there is location, it is not just one symbol we will be reading, we will be reading a column of symbols based on the number of tracks available. So more the tracks, suppose if I am having n number of tracks available in my tape, there will be n number of that is symbols read from the tape at a time. So even though we are having multiple tracks, the tape is going to be unique, and it means that there is going to be only one finite control available. So at any point of time, a read operation is going to read a vertical, there is cells, vertical list of cells, or it is going to be a column completely read by the finite control, and you can either make use of those symbols, or you can, even if you want, you can record symbols, or you can make use of tick marks saying that whether a symbol has been already processed or not. So, for everything we can make use of the remaining tracks. Moreover, normally when we are given a there is input, one or more number of inputs. So, what do we do is we will rewrite the input. Later we will be left with we will be losing the input at the final stage of the computation or even the recognition. But these kind of issues can be rectified provided we have multiple number of tracks on the Turing machine tape. So, we will be making use of one or more number of tracks for us marking for the purpose of marking whether a symbol has been already processed or not. So, if the symbol has been already processed, then we can claim that that is some tick mark symbol will be introduced on the corresponding that is column, but in a different track. So, we will find that really it is useful for that is keeping the input intact even that is after solving the problem or even after doing there is the termination. We will make use of that kind of that is tracks. Here it is the description of the track. So, contains several tracks, but there is only one head. As I told earlier, that is going to be the head is going to be unique, and the tape is going to be that is the tape alphabet. Every time it is going to be a tuple with one or that is common with one component for that is each track. But what will happen for the Turing machine that is power is whether it is going to be a single track Turing machine or it is going to be multiple number of tracks or one storage location or multiple storage locations, whatever it is, we will find that the Turing machine power is not at all changing. That is the Turing machine, that is language recognition power, that is whether it is going to be a Turing machine with a single track or with multiple tracks or with no storage or with storage on finite control, the power of the language is remaining same. That is always recursively enumerable if the halt is not guaranteed, and it is recursive if the halt is guaranteed. Here we shall see that is how the multiple tracks are being handled. So, this is what the Turing machine tape. So, normally the Turing machine tape is going to be infinite on both directions. Here the only the input is shown. We have A, B, C, D, then D, C, B, A. So, actually it is going to be a palindrome that is string. In the previous episode, we have solved this problem by replacing the first, read the first symbol, make it as blank, record it in the storage, and move towards right, find out the blank to know what is going to be the very last symbol available in this input, and we will ensure that it is going to be valid move provided the symbol recorded in the finest control, that is storage, is same as the symbol one is available on the last point of at the end of the input. So, what we will be losing is this first symbol is made as blank, and the corresponding symbol from this tape is also made as blank. So, ultimately we will be losing the entire that is input at the end. We will be able to say that whether the string is going to be a palindrome or not, but we will not be able to restore what the string for which the result has been declared. So, that problem can be that is solved by introducing multiple number of tracks. So, we will be introducing a similar track, an additional track along with that. Initially the entire content of the additional track is set to blank. So, now here is the situation, like we have that is A, B, C, D and D, C, B, A, that is string which we want to verify. So, once we have, so starting with Q0, here it is going to be Q0 comma A is the symbol, and what we should do is the second track of the Turing machine is now recorded with a tick mark. So, del of Q0 comma A comma blank is the input. Now, the output is going to be maybe some new state, that is Q1, and what we write is leave that A as it is, but the blank on the second track has been replaced by a tick mark. So, we will have the A and followed by tick mark. So, now we move towards the rightmost end of your tape to find out an unticked symbol or an unmarked symbol that will be known after knowing either a blank on the second track or a tick mark already on the second track of the input. So, here we have the situation like A and B are already ticked, and here A and corresponding B are already ticked. So, now if we are starting with C, so we will be going for a tick symbol, keep moving until we find the very first tick symbol on the right. Once you know that, you move little, there is one position towards back, and we will find that C. So, here you can check whether it is going to be C and C. If it is going to be C, then here also we can make a tick mark. So, finally, if there is any unticked symbol whose corresponding symbol has not been identified, then the Turing machine will be halting without acceptance. And if it is like all the symbols have been ticked and its corresponding symbols have been identified, and it means that the Turing machine is going to halt with acceptance. The prime intention of the introduction of the multiple track is not for extending the capability of the Turing machine, but the design of the Turing machine will be much easier for problems like the strings represented in the Turing machine tape, which we do not want to lose even after recognition or even after finding the result of the computation or the recognition. So that is what the idea. So we have the description here, that is the additional tracks may be used for checking of symbols, and it is not necessary to modify the input values. So that is what the application of the Turing multiple tracks on the Turing machine. Still we should remember that the power of the Turing machine is not at all changing, whether it is going to be one track or more number of tracks available on the Turing machine. So there is one more facility we have called the subroutine facility. So subroutine is going to be a small piece of that is the Turing machine, which will be doing some well defined job, and that can be reused for any number of times. So similar to the programs and where we are making use of the subroutines or the functions, which will be reducing the amount of lines of code which is available in source code. Here also we will be making use of the subroutine kind of scenario, which is actually reducing the complexity in the design of the Turing machine. You can design the Turing machine in pieces and or subparts, and then we can make a jump just like making a call in a program to a subprogram, and there will be a state which is not having any valid move, which will be considered as a return point as far as subroutines are concerned. So it is just like transferring the control from a state to the start state of the subprogram, and once we reach a state for which there is no valid move, it denotes that a return point, and for that state there are valid moves available as far as the main routine is concerned. So once you reach the end of the subroutine, it is implicitly transferring the control to the main routine, from where we will be making transitions saying that the actual return process or the main program continues its execution. So that facility is available as far as our Turing machine serial is concerned. So it is going to be a set of states doing some useful job, and there is a state called start state, and there is another state with no move. So the no move state, actually it is meant for denoting a return point, and the call is happening, that is we can say that the Turing machine calls this subroutine whenever we are in the start state of the subroutine. So the state without any move, it is behaving just like a return point. Actually the state which is not having any move in the subroutine will be a state in the main routine where there will be valid moves available. Then only we will be able to resume the continuation of the main routines statements or the various states. So the simplest example we can quote for this is, you can see the multiplication as repeatedly adding the second argument for the first argument number of times. So that is what the idea. Multiplication can be thought of as calling add required number of times. So we will be writing a routine for add, then we can make use of this add routine repeatedly for carrying out the multiplication. We have the Turing machine for this multiplication routine, where the routine which is carrying out this add operation will be called, that is the copy operation. So in general, the Turing machine for subroutine looks like this. We have a start state for the Turing machine, and we have a state from where we will make a call to the subroutine. So the state, from there is a jump to qi, which is going to duplication of the state, so which is nothing but the start state of the subprogram, and from there we will be going to a state called qk, and from qk there is no valid move, but this state qk is once again repeated as far as the main routine the main Turing machine is concerned. So from there are valid moves available, so that will take you to the final state of the Turing machine. So here we have, there is a return point, we just return it to the that is qk, and from there we can reach, based on the available transitions and the input, we will be able to reach the final state. So that will take the entire, that is the design much simpler. We can design the subprogram separately and the main routine separately, we can make a jump to that and return. So you will be getting the results done, and that is back to the main routine. So that is what the subroutines are all designed, and how we are doing the computation with the help of the subroutines. After a short break, we will continue this lecture. Welcome back after the break. So we have the Turing machine, which is for multiplication. So for multiplication we need actually two inputs. So one is going to be the integer called m, and another one is going to be the integer called m. That is, starting the input is loaded into the Turing machine like this: 0 power m followed by a 1 and followed by 0 power n. So this 1 is used as a separator, saying that m and n are the two inputs. And after multiplication we wanted to have a result, that is this m into n in unary form, that is 0 power m n. So m into n number of zeros only should remain on the tape at the end. So now what is the role of the copy routine, or what is the role of the subroutine which will take care of the copy operation? So the idea is like when you are having 0 power m followed by a 1 followed by 0 power n, you pad this 1 1 here just for separating the arguments from the partial result. So first you take this 0, very first 0, make it as blank because it is not at all needed at the end. So make it as blank. Immediately you go to the second argument, you find out how many number of zeros available. For every 0 from the second argument, you copy 1 0 at the end of the tape. So you go to the end of the tape and find out the blank, replace it by 0. So when you are doing that process, there is a need for counting how many zeros from the second argument have been copied so far. So there is a need for something like check mark, like you can go for the multiple tracks like that, or you can replace this by some x or y, and after copying once again we can restore this input to the actual zeros, that is 0 power n. So how we are doing that is, that is, we have the copy routine description here. At any stage we will start with this configuration, that is already k times multiplication has been done. So what will be the result is, actually we need to multiply n m times, but here the result is n k times available. It means k number of times we have copied the n number of zeros at the end of the input. So what remains in the first argument is m minus k number of zeros available in the first argument, and in the result k into n number of zeros are available there. So now what should be done is, get the next 0, that means the k plus 1 0, make it as blank, and the second input leave it as it is, to give a new output k plus 1 times, that is n. If this is the initial configuration of the copy routine, then the copy routine is expected to give this as the resulting configuration. So rest of the things will be taken care by the main routine. So you just ensure that this is your input and then move to the produce this as the resulting input. So the idea is, get the first 0 from the second argument, replace it by x, go to the rightmost end, find out the blank, replace it by 0, come back, find the x, next to that whatever is available, 0 is available means you replace it by x, then go to the rightmost end, replace the blank by 0, and keep doing until we find that no more zeros available in second argument. So in that case, when you traverse from right to left, after seeing this one, the separator which is separating the arguments from the result, when you are traversing towards left, replace all these x's by zeros, giving you 0 power n back in the input, so that it will be further used for the computation or the copying in the remaining times. Let us see that is how this copying is carried out here. We start with the state that is q0, and I said that the 0 available in the second argument is to be replaced by x. So we are moving towards right. So now this 0, that is whatever the 0 just we are replaced by x, should be copied onto the rightmost end of the tape. So for that you just keep all the remaining zeros. So 0, leaving it 0, move right. Then one time we will get a 1 saying that that is going to be the beginning of the result. So 1, you leave it as 1, move towards right. Next once again we will be having some number of zeros. So 0, leave it as 0 and move towards right. But how long this is going to happen? Once you reach the end of the tape, we will find a blank, and now we have to add one 0 onto the rightmost end. So for that we will replace this blank by 0, and after that there is nothing to do on the right, so you are making a move towards left. When you are moving towards left, you skip all zeros. So we are having zeros replaced by, leaving as it is but moving towards left, and there is a chance for having a 1, but it is going to happen exactly once because it is the 1 used as separator for separating the input from the output. You leave that 1 as it is, still it is going to be moved towards left. Once again we may have some number of zeros, so leave that 0 as it is, move towards left, but after some time we will find an x. So that is marking the beginning of the remaining zeros available in the second argument of the multiplication. So leave that x as it is, but it is going to be right move first 0 from the remaining component of the second input. So that is what the state where we are having it, q1 is there. So it is going to be cycle. Get the 0, replace it by x, skip all zeros and ones, find the blank, replace it by 0, then once again skip all zeros and ones, move towards left, find the x, once again starting point. So now the question is, when do you complete the process? From q1, when you are looking for a 0, if there is only a 1 available instead of a 0, then it means that all zeros from the second argument have been copied onto the rightmost end of the tape. So there is no more copying process. So start from q1, if you are finding a 1, leave that 1 as it is. Now it is going to be a left move, and that left move will give you x, because if there are n number of zeros, all those n number of zeros have been already made as x. So when there is a move for left, then we will be exposing that x. So now what we should do is, these x's are the unary representation of the second argument, that is n, which was earlier in zeros form, now it is all in x form. So they all should be replaced by zeros. So as long as x is available on the tape, we stay back in the state number q4 and replacing x by 0, restoring the second argument, that is n, in terms of n number of zeros. So x leaving, that is replaced by 0, leaving moving towards left. And how many number of x, that is after replacing all these x's by zeros, we will be in a position to, that is find a 1, which is the separator for m and n. So that separator should not be disturbed. So the separator, that is 1 separating, that is m and n, should be left as it is, and now it is going to be a right move. So now you are in q5. So the q5 is going to be a state from where we find there is no outgoing transition. It means that it is going to be return point. So once you reach the return point, then it will take you to the main routine of your Turing machine. So to summarize the copying process, we start with 0 power m minus k, 1, 0 power n, 1, 0 power k n. After some number of steps, that is after repeatedly doing these steps, we will be having 0 power m minus k plus 1, 1, 0 power n, then 1, 0 power k plus 1 into n. This is what the output of the copy process. So when we see that is q1 is the state, that is going to be the entry point for the subroutine. There is a call equivalent to generating a call, and the q5 is the state, means it is going to be a return point from where there is no outgoing transition as far as this copying is concerned. Now let us see that is how we are doing this multiplication, or this copy routine is made use by the that is your multiplication routine. Here is a starting point, the multiplication starting point. So we have that is q0, and the input is going to be 0 power m followed by a 1 followed by 0 power n followed by a 1. So now that is read the first, that is the input, find out the first 0, make it as blank. After that what should be done is, we are in a state called q6 where it is used for skipping all the zeros from the first input. So 0, leave it as 0, move towards right. So 1 0 from the first input has been made as blank. Now we have to go for copying n zeros from the second argument to the end of the tape. So for that we are making a jump to the starting state of the Turing machine, that is subroutine called copy, which is nothing but the Q1, and it does the job of entire copying process or addition, and finally we will be in Q5. So this Q5 is the state which is actually the finite control is staying at the end of the second input. So now we have to come back to the beginning of the input. So by skipping zeros, that is 0, leave it as 0, move towards left, and now we are in a state called Q7. From there, if you find a 1, you leave it as 1 and move towards left. So we are in the state called Q8. So once again we have to go for skipping all the zeros. So 0, leave it as 0, move towards left, and as long as more zeros are available, that is leave them as zeros and skip towards left, that is move towards left, and when you find a blank, that is one cycle has been over. One cycle, I mean one time multiplication has been over as far as the sequence of states like Q0, Q6, Q1, Q5, then Q7, then Q8, and then it is going to be Q9, and from there it is Q0 is concerned. So it will keep on doing, that is making the a 0 from the first argument as blank and copying n number of zeros at the end of the input. So now you look at the stage that is Q8, where we find that there is no more 0 available on the first input. It means when you are looking for a 0, instead of finding a 0, we find a blank. It means the entire copying, that is the number of the copying for the required number of times have been it is already done, and now instead of getting a 0 from the first argument, we find that there is a blank available. So you leave the blank at is and then move towards right. So the situation is now like we will be having that is no 0 from the first argument, but the entire, that is zeros from the second argument, are residing still on the tape. In the beginning there is a 1 available, which is actually the separator for m and n. So that should be completely made as blank. So we are just making the separator as blank, and then we are making the ones, the zeros available in the second argument as blank by using the state called as Q11. And once the complete zeros have been made as blank from the second argument, there is only one pending, and you make that one also as blank and move towards either right or towards left, whatever it is. At the end we will find that the entire multiplication has been done. M into n is there on the tape where we stand by the state called that is Q12. So the description here, the how it is being carried out here is, we start with 3 multiplied by 2 here, that is the input, and after some number of steps, actually we started by replacing this 0 by blank, it is done. It means that one time copying is going to happen now. So it is B, and now remaining 2 number of zeros are available. So these 2 zeros, that is from the second input, are made as X, and corresponding copying has been done. Actually here we have nothing as far as the right of 1 is concerned, but after making these 2 zeros as X's, we find 2 more zeros paired around to the that is rightmost end, that is copying does. Now we have to restore the input. To restore the input, these 2 X's must be made as zeros. So B 0 0 1 0 0 then 1 0 0. So this is going to be the copying after this one time copying, the result after one time copying. Then it is second time, we have 2 more zeros. Then it is going to be third time, we have another 2 more zeros. So now it is the case where there is no more 0 in the first argument, but the second argument is now available on the tape. So you make it as blank, zeros, all zeros as blank, then this 1 also as blank, leaving exactly 6 number of zeros as far as the tape is concerned. So this is what we are doing as far as the multiplication with the help of Turing machine is concerned. You just whatever it is, it is not necessarily the multiplication, even it is going to be a mod operation, or it is going to be an exponentiation, or even division. So whatever is needed for us, you just divide the problem into, that is sub problems, and for each sub problem you construct the Turing machine in an individual manner, and then we can make a jump to the, that is the starting state of the sub program, and keep one state as the state in the subprogram with no outgoing transition, saying that is going to be the return point. So that is what the construction of Turing machine of the subroutine. And as far as the questions component is concerned, so we have seen the problem which is actually multiplying two integers. Now it can be the mod operation, which is keep on dividing, and so here is very small change we have to do on this Turing machine what we have done for the multiplication. It is going to be the subtraction kind of that is operation, and the second argument every time we are reducing from the first argument. So we need to find out how many more number of zeros pending. So if you could find out that the second number of times of zeros, we will be able to find out, no problem. But if it is failing, then we have to restore how many number of zeros we have that is made as blanks to these zeros. So that is going to be the result of this mod operation. Another thing is like the exponentiation. So it is going to be the repeated multiplication. Having done a routine for multiplication, you make the entire thing as a subroutine, and then we can introduce some more states to say that the multiplication is going to be called that is some number of times. So that is about your exponentiation. So you just divide the problem and write the or design the Turing machine based on the subproblems. So you will be able to find out the Turing machine, or you will be able to construct the Turing machine with the easy manner. So with this I conclude this episode. Thank you all.